10.2, the integral test and p-series test. In the last lesson, we explored methods for finding the exact sum of geometric and telescoping series. In the next several lessons, we want to focus our efforts on whether or not a series converges to a sum, and not necessarily find the value of that sum. So that is really important for you guys to pay attention to, that we are basically just looking for convergence and divergence, or I should say convergence or divergence, not really worried about to the sum that it converges to. Now, when we were looking at the geometric series test, we actually had a way to find the sum that it converges to. So that one we were able to find. But the ones that we're going to be doing, some of them we might be able to find the sum, and some of them we just will find out whether it converges or diverges. So the convergence tests that follow apply to series with positive terms. And so far we have seen two tests. They are stated here. The geometric series test is the first one. And I wanted to talk about this real quick. A geometric series is in the form, if you start at n equals 0 when you're doing a summation and you see that you've got something to the nth power, you know that when you put that first value in, it's going to give you a, right? And then the second value is going to give you a times r. Because this is corresponding to when n equals 0, and then this one would be when n equals 1. So that is when n equals 0, what you're going to have a times r to the n. When your n equals 1, and you have a times r to the n minus 1, when I put that first n equals 1 in, I get r to the 0 power times a. So again, I get that first term that is a. My second term, when I put 2 in for n, I will get that ar, which is what I want to get, for your first and second term. This one just gave it to me when n was 1, the second term when n is 2, because of how it was stated here with the n minus 1. The next one that we have, summation n equals 1 to infinity of a times r to the n plus 1. When I put my 1 in, I get a r to the second. Uh-oh. What does that mean? This is supposed to be a -1. Because you want your first term to always just be a. So, on your paper, please change this lower limit to start at -1, okay? Because then if this one is -1, which, let me just change it again here. When I put my -1 in, I get a times r to the 0, and that will give me a. When I put my 0 in, I get a times r, and so on and so forth. So your summation should always, the very first one should always start with a. And I will show you what I'm talking about when we get down to that example number 1. Now, a is your first term of the series, r is your common ratio. The geometric series diverges if the absolute value of r is greater than or equal to 1. If the absolute value of r is between 0 and 1, then the series converges, and it has a sum a over 1 minus r. Okay, and that was when I said that, yes, you can tell us what it converges to if it's geometric. The nth term test for divergence. Anytime you see a summation like this with n's in it, do a little quick limit as n goes to infinity to see if you get 0. If you don't get 0, then your summation is going to diverge, okay? So we're going to talk about that when it comes up. But just if you do get 0, it doesn't mean it converges, but it could converge. But if you don't get 0 when you take the limit as n goes to infinity of that nth term, if you don't get 0, if you get some finite number, you can say that your series diverges. Okay, so I'm going to go ahead and change my color here. We're going to determine whether the following series converges or diverges. So the first thing I'm going to do is just look at what happens when I have 1, when I put 1 in. When I put 1 in, I get 4/25. 4/25 has to be my A, okay? So I'm going to, that's just my first term. So I'm going to look at what I can do with this function so that I will be able to see my A. So I notice that if my n is positive 1, that my r should be taken to the n minus 1 power. So right now, I've got 4 to the n. I've got 5 to the n times 5, okay? So if I could somehow make this 4 and this 5 to the n equal my n minus 1, that would be perfect. And so since I would need a minus 1, I would like to, and this is one way to do it. You don't have to do it this way, but if you make that 4 times 4 to the n minus 1, since this is 4 to the 1, and they have the same base, and you would add your exponents, the positive 1 and the negative 1 would go away, and you'd be left with 4 to the n. And we're going to do the same thing, 5 to the 1 times 5 to the n minus 1, and then there is an extra 5 down there. Okay, I just took that 5 to the n and did that. So now we can see that we've got summation n equals 1 to infinity of 4/5 to the n minus 1, and then what's left is 4/25. So this is a times r to the n minus 1. So now I can see that my r is 4/5. Okay? And so since 4/5 lies between 0 and 1, this converges. So since 4/5 lies between 0 and 1, the summation n equals 1 to infinity of, I'll go ahead and put the a first, 4/25 times 4/5 to the n minus 1 converges. We don't know what it converges to, but it converges. Since it's geometric and it converges, we can actually find out what it converges to. And so we're going to go ahead and calculate the sum. So our sum is our first term, 4/25, divided by 1 minus our r. And so 4/25 divided by 1/5, because this would be 5/5 minus 4/5 is 1/5, and that would be 4/25 times 5/1, divide by 5 I get 1, divide by 5 I get 5. So it actually converges to 4/5. Okay? Oh, goodness. So we got that by just using our formula for the sum of a convergent geometric series. If it wouldn't have been convergent, of course, we couldn't have used the sum. But it was convergent, so we were able to. All right, so now we're going to do letter B. I'm going to do that in a different color, sorry. So for this one, you can see that if you took the limit using your nth term test for divergence and looked at the limit as n goes to infinity of 5n squared plus 3 over 2n squared, and you're like, wait, I know how to do this limit. If it's an n behavior limit, I can focus on the lead term in my numerator divided by the lead term in my denominator. They're so strong that I know that my function or my, whatever this expression is going to be so strong, it will lead it. And when I do that, it gives me the limit as n goes to infinity of 5/2, which I know then is 5/2. So this limit converges to 5/2. That is not 0. Therefore, by the nth term test, for divergence, the summation is n equals 1 as n goes from 1 to infinity of 5n squared plus 3 over 2n squared diverges. Okay, and so on A we used the geometric test, and on B we used the nth term test for divergence. And that was just practicing those two. Okay, so when looking at the first few terms of a sequence of partial sums helped us with geometric and telescoping series, we will see many cases where this won't help. That means you will need to be skilled at using all of these tests. So I feel like you understand the geometric and the nth term test. And today on this lesson, we're going to study these two, okay? And then on the next lessons coming up, we'll do the next 4. So exploring the integral of a series. The integral test allows us to compare a series to its integral in order to prove convergence or divergence. So we will be able to prove whether a series is convergent or divergent based on the integral that looks just like the series. So let's explore the idea by completing the table below for 1 over x squared. So f of x equals 1 over x squared is a function, okay? And then we're also going to compare it to f of n equals 1 over n squared. Now remember, this is a series, and for series, the domain of a series is the set of positive integers. So it doesn't have things in between like 1 and 2. You know, it's just at 1, you know, so your domain is just like 1, 2, 3, 4, 5. That's your domain of a series, okay? Where the domain of this function is everything but 0. So it includes everything in between. But on a series, your domain is always just 1, 2, 3, because it's like the first term, the second term, the third term. So let's look at the function, okay? And when I put 1 in, 1 over 1 squared is 1, 1 over 2 squared is 1/4, 1 over 3 squared is 1/9, 1 over 4 squared is 1/16, and 1 over 5 squared is 1/25. And so I've got my function values. You can kind of see here the way they've, you know, went from 0 to 0.25, 0.5, 0.751. And at 3, the value is 1/9. At 4, it's 1/16. At 5, it's 1/25. And so they've got everything there. Well, it just so happens that when I look at my series, since it's 1 over n squared, it's going to have those values. It's just not going to have everything in between like the 1 over x squared does. So when I put in my, 1 over 1 squared, I get 1, 1. When I put in my 1 over 2 squared, I get 2, 1/4. When I put my 1 over 3 squared in, I get 3, 1/9. So these blue points are actually points on your function and on your series. And so what it wants us to do is draw the right-hand sum with 4 partitions over 1, 5. And so if I'm starting out here, this is like my starting point at 1. And I'm going from 1 to 5. If I'm doing right sum, I would go here and then calculate this area. I would go here and calculate this area. I would go here and calculate this area. I would go here and calculate this area. Each one of these has a width of 1. And so when I take the area, 1 times 1/4, right? Plus, and then we have 1 times 1/9, plus 1 times 1/16, plus 1 times 1/25. This is my RRAM. This would be your RRAM for the function. f of x, but it just so happens to be my partial sum, but not including the very first one, okay? So this is the sum of the second term, the third term, the fourth term, and the fifth term. But if I put that in my calculator, I get 1669 over 3600. Approximately 0.4636. So, that's what's going to happen for your, this is your RAM for f of x, but it just so happens that these values right here are all the values for the range of my f of n. So if I was doing the fifth partial sum, well, my first one is 1, my second one is 1/4, my third one is 1/9, my fourth one is 1/16, and my fifth one is 1/25. Okay, so that would be my fifth partial sum that we say S sub 5 for the fifth partial sum. And if you put that in your calculator, you get 5,269 over 3,600. And that is approximately 1.4636. So notice that if I took this very first one off, if I subtracted off that 1, I would get my RAM, okay? So now we're going to compare that to what if we took an integral from 1 to 5, okay? So if we took an integral from 1 to 5, we know how to integrate. So I've got from 1 to 5, I'm going to change this to x to the negative 2 dx. So this is going to be x to the negative 1 divided by negative 1 from 1 to 5, which we're going to make negative 1 over x from 1 to 5, which gives us negative 1 over 5 minus negative 1 over 1. So this is a negative 1/5 plus 1, so that's going to be 4/5. And so we also know 4/5 as 0.8. So if we were just summing up from 1 to infinity, just these values, and we didn't include this first one, this is going to be an upper bound for that summation, okay? Because look, you can see, I'm going to do this in green. You can see that when we integrate, it's going to give us a bigger number, because look, we've got all this extra. And like I said, we are not counting the first term. This is not counting that first term in the summation. And it is okay to do that sometimes. If you're trying to figure out convergence or divergence, sometimes you have to let things go and not include it. And so if we're just looking at, like what this does as it goes to infinity, we can look at, that it is converging, okay, to a value. Your integral here converges to a value, and the integral test says if your integral converges, then your summation converges. So this is what our integral test is going to tell us, that this converges. We don't know what it converges to, but we know it converges, okay? And we will talk about an upper bound. We just aren't ready for it until we start talking about the remainder. But you can see that, without counting that first term, that this is an upper bound for the values from 1 on. Okay, so integral test. To use this test, f must be continuous, positive, and decreasing on the interval from 1 to infinity. So, and then if this integral from 1 to infinity of f of x dx is convergent, then the summation is convergent. If it's divergent, then the summation is divergent. Now, the only thing I did not talk about was checking, if you're going to use the integral test, checking to see that it's number 1 continuous, number 2 positive, and number 3 decreasing. So this one specifically says to apply the integral test to each of the series below. So I do need to check to see if it's always going to give me something that is positive. And if you look at this, it's any end that you're putting in, we're putting in all positive ends, but it's going to always give you a positive value. Now I have to decide, is it continuous? Well, there's nothing that will give me -1 here that would give me division by 0, so it would be continuous, okay? And then lastly, is it decreasing? Well, you've got your ends going in, and they're getting, bigger and bigger and bigger. Your numerator stays constant. So therefore, yes, the entire thing is decreasing. And this is true on that interval from 1 to infinity. And sometimes it might not be true, for like, negative infinity to -1 or something like that. But it, you're just worried about the 1 to infinity interval. Okay, so you do have to look at that. So once you've determined that it is positive, continuous, and decreasing on your interval, then we would say, okay, I want you to consider the integral from 1 to infinity, 1 over x squared plus 1 dx, because all of these values are going to be exactly the same. And so this could be a good function to compare it to see if this one converges, then my summation is going to converge. So we're going to say, okay, this is an improper integral. Dx. So we had to change that to a limit because it was an improper integral. And so now we're going to say, oh, this is inverse tangent of x from 1 to b. And so we are going to look at inverse tangent of b minus inverse tangent of 1. And then we'll take that limit. We'll look at it as limit, or as b goes to infinity. So now think about what inverse tangent function looks like. Okay, if I was trying to remember what my inverse tangent of x looks like, I would remember that there is a vertical asymptote at, a horizontal asymptote at pi over 2 and one at negative pi over 2. And my inverse tangent function looks like that. So as my ratios go to infinity, you can see that your inverse tangent is going to approach pi over 2. So I'm going to say that the inverse tangent of b as b goes to infinity is pi over 2, minus the inverse tangent of 1. Well, for what angle is the tangent 1? That would be pi over 4. So, and oops, I already put that in, so I'm going to take that off of there. So this is going to end up giving you pi over 4. Now, that doesn't mean that that is what your summation goes towards. All this means is that your 1 over x squared plus 1 converges. And so by the integral test, your summation converges. Okay? That's what we're telling you, that if this equals a finite number, then your improper integral converges, and so therefore your summation converges. Okay, so for the next one, I look at this one and I think, okay, well, it definitely does have a limit as n approaches infinity of 0, but that does not tell us whether it is convergent or not. It just, we know we can't use the nth term test for divergence. So now, how about if I use the integral test? Since it's asking me to use the integral test on each of those, I need to check to see, is it always positive? And if I put, I'm going from 1 to infinity, so n is always going to be positive, and then I'm going to take it and square it and add 1 to it. So yes, it's always going to be positive. Is it going to be continuous? And since n squared cannot be -1 by any means, then you're not going to have division by 0. So that means it is continuous for all values. Okay. I forgot my u. And then the last thing, is it decreasing? Okay. So since you are putting, like 1 over 1 squared plus 1, so that'd be 1/2. 2 over 2 squared plus 1. That denominator is getting bigger quicker than the numerator, okay? So it's always going to be bigger because, 2 over, and this would be 5. So yes, it is going to always be decreasing. One way to prove that something is decreasing is to take the derivative and show that for our interval from 1 to infinity, that the derivative is negative there, okay? That's another way to show that a function is decreasing. But since we could kind of talk our way through it, we didn't have to worry about it. So we are going to consider the integral from 1 to infinity x over x squared plus 1 dx. And if you do this, I would probably use u substitution and put x squared plus 1 in for u. My du would be 2x dx. So du over 2x is my dx. So this would be the integral of x over u times du over 2x. The x's will cancel. I'll pull that 1/2 out in front. Now, I did not put my 1 to, and I forgot my limit, sorry. Limit as b goes to infinity. But I did not put my, my 1 and my b back in because I want to look at leaving my u alone. So 1 squared plus 1 is 2, and then b squared plus 1. So 1/2 limit as b goes to infinity. This is going to be 1 over u du, the ln of u from 2 to b squared plus 1. So 1/2 limit as b goes to infinity, ln of b squared plus 1 minus ln of 2. And if you put infinity into ln of b squared plus 1, this is going to go to infinity. So if one of these goes to infinity, this is going to diverge. So since your integral diverges, therefore your summation will diverge. Okay, so this one is divergent. This one diverges. Okay. So now, comparing two series. Let's explore why 1 over n squared converges but 1 over n does not. Consider the following groups of terms in the harmonic series and show that the sum of each group of fractions in the series is more than 1/2. So if I look at just this first one that's in parentheses and I take the sum of it, it's 1/2. If I look at, so that was it was my first one. If I look at the second one and I add the 1/3 plus 1/4, I'm going to get 7/12, and that is greater than 1/2. Now, if I take this third group of numbers and I add them in my calculator, I got some big numbers coming up here. 533 over 840, and that is greater than 1/2. And then this last one, the fourth one, I should say, I got 445,007 over 360,360. And that is greater than 1/2. So, it asked us to show it. We just showed it by just giving the sums. Now consider the terms in the series, summation 1 over n squared. So if I put a 1 in, I get 1. If I put a 2 in, I get 1/4. If I put a 3 in, I get 1/9. If I put a 4 in, I get 1/16, and on and on. It says group the terms after 1 in any way you would like, and show that they are never greater than 0.65. So the first one, I kind of did it like the one above. I put a parentheses around the first one, and I said, okay, for my first one, it's just 0.25, which is less than 0.65. And then for my second grouping, I think I did these two. So this was 1, and I think my second one was 1/9 plus 1/16. And I put it in my calculator, and I got 0.1736, which was less than 0.65. And then for my third one, for some reason, I think I took the whole thing here and made that my third one. Oh, sorry. And for that one, I got 0.2414, and it was less than 0.65. So explain why the harmonic series never converges. Since you're adding 1/2 plus, a number greater than 1/2 plus another number greater than 1/2, your values for 1 over n, and by the way, that was an equal sign there, sorry. They're just going to keep going and going and going. They're going to keep getting bigger. But for the 1 over n squared, those values are staying very small. And they're going to get even smaller as you keep getting another n, because your denominator is getting larger, which means your number is getting smaller. So we are going to say after the second term, each grouping of 2n terms will have sums greater than 1/2. Which is the value of the second term. Therefore, the sums go to infinity and diverge. And again, this is talking about that harmonic series, which is our summation 1 over n. It does diverge, and 1 over n squared converges. So that is a kind of something that you need to remember, and you're going to be using that when you're doing convergence and divergence. Okay, our next thing is the p-series. A series in the form of summation n equals 1 to infinity, 1 over n to the p is 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p, dot, 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 1 over n to the p is called a p-series, where p is a positive constant. For p equals 1, summation from n equals 1 to infinity, 1 over n, this is the harmonic series, and it diverges. So here we've said if p equals 1, that's the harmonic series, it diverges. And so, but what happens is if you have a p series, something like this, 1 over n to the p, if p is greater than 1, it's going to converge. If p is between 0 and 1, it's going to diverge. Or, of course, like we said, if p is equal to 1, it's going to